Hello and welcome to the Hydrocarbon Engineering Podcast, the podcast series for professionals in the downstream refining, petrochemical and gas processing industries. I'm your host, Callum O'Reilly, and in this episode I'm sitting down with Klaus Brun, Global Director of Research and Development at Ebara Elliott Energy, to discuss his article that featured in the February 2025 issue of Hydrocarbon Engineering magazine. Titled High-Speed Hydrogen Compression, this article considers the progress that we are making towards adapting centrifugal compressors for high-speed hydrogen compression. I hope you enjoy this episode. Welcome, Klaus, and thank you for joining me to explore the subject matter of your recent article that featured in the February 2025 issue of Hydrocarbon Engineering magazine. I'm really looking forward to getting your thoughts on the current state of centrifugal compressors for high-speed hydrogen compression and the progress that the industry is making in this area. But before we get started, please can you tell our listeners a little bit about yourself and your current role at Ebara Elliott Energy?
I'm currently the global director of R&D, which really is a misnomer. It's all product development within Ebara and Elliott Energy company. My organization is in charge of product development for compressors, steam turbines, pumps, cryodynamic expander, cryodynamic pumps. So a fairly large set of products. The primary focus of our company and my job is obviously turbo machinery. So that's my background and the area of my responsibility.
Great. Thank you for that, Klaus. So I thought we could start today's conversation by talking about the global transition to carbon-free energy by 2050. What do you see as some of the major challenges to achieving this?
The biggest challenge is that our current energy infrastructure isn't decarbonized, right? I mean, if you look at the global world energy demand, it's probably about 10 to 15% or so is decarbonized in the sense that it's nuclear or it is alternative energy, wind, solar, hydro, etc. But roughly about 80% of the total world consumption is fossil fuel based, right? So you're producing carbon dioxide. That's what we're talking about here. And so really you have two challenges. One is you have to either replace the existing energy infrastructure, which is the big challenge, right? Or you have to decarbonize the existing energy challenge. So on the one side, you're looking at electrification, you're looking at hydrogen, you're looking at hydrogen carriers. On the other hand, you're looking at the decarbonizing power plants, aviation, transportation. You're looking at decarbonizing all of that, which really means taking CO2 and transporting it and geologically sticking it into some kind of formation, which is also very challenging. None of that infrastructure currently exists from our perspective. Some of the turbo machinery is a small engineering challenge, and some of the turbo machinery is a significant engineering challenges. But it's not just the design, but it's also the manufacturing. You have to start talking about very different compressor pumps, geometries that are really not in existence right now. And then you have to look at aftermarket service and all that kind of stuff. So it's not just the development of a new machine, but it's also manufacturing, the servicing, the entire ecosystem that you need for the turbo machinery that doesn't exist for these kind of machines. So it's easy to say we're going to convert by 2050, but there is a significant lag, not just on the electrification side, but also on the turbo machinery side and on the pipeline side and all the associated industries that need to be converted to that.
So while the most common forms of non-electric transported energy today are fossil fuels, we're obviously in the midst of a transition at the moment. I was wondering if you could talk us through some of the options that are available and their relative pros and cons.
I mean, it's probably worth stepping back and talking more fundamentally from an energy transport perspective. There's obviously electricity, and we're not going to talk about that. That's an obvious one. But then there is really your solid and your fluid. And your solid is basically coal and biomass, right? Coal and biomass both have a very high ratio of carbon to hydrogen, meaning you're producing a lot of CO2 per energy that you're getting out of them. So that's bad because we want to minimize the amount of CO2 we put into the atmosphere. So CO2, if you burn it, emits a lot of CO2. Biomass does the same kind of thing. And then you're looking at your fluids. And so your fluids are either your liquid or your gases. From that perspective, the best one is actually methane, right? Because it has CH4, which means it has a lot of hydrogen or carbon. And so it has a very good hydrogen carrier in the sense that it doesn't emit a lot of CO2 per hydrogen that you have. And then you're really looking at what we consider to be the future, which is hydrogen and other hydrogen carriers. Hydrogen you can transport either as pure hydrogen that can be compressed, but hydrogen, and we'll talk probably about this a little more later, but hydrogen is difficult to compress just from a turbomachinery perspective. Thermodynamically, it's not easy to compress. It has a low density, very high specific heat. It is very flammable, low emission energy. It's dangerous as a gas. Then you have other things that are hydrogen carriers, and those could be liquids or they could be gases. For example, on the liquid side, you have ammonia, and that's kind of great because it doesn't have any carbon associated with it. It's NH3, but it is toxic. It is caustic. It will kill you. It is corrosive and has a lot of dangerous and other side issues that make it less comfortable for transportation. Then there's other liquid hydrogen carriers that do involve carbons, for example, ethanol, methanol, dimethyl ether. And for all of those, you're dealing with CO2 emissions. Either you put the CO2 in there and then you take it back out, or you just burn it and you end up with CO2 in the atmosphere. Again, there's a lot of options out there. You can also liquefy hydrogen. Hydrogen liquefy that about minus 430 degrees Fahrenheit, so just slightly above absolute zero. That's possible, and the technology for that exists. It's being used for a space shuttle, for example. But the problem with that, it takes a lot of energy to liquefy hydrogen. So you take about 30 to 40% of the energy of the hydrogen itself to just liquefy it. So that's a tremendous waste of energy. And in a sense, the same happens with hydrogen compression. It takes a lot of energy to compress hydrogen. So there are no really easy options to transport these carbon-free energy carriers. Hydrogen is obviously an energy carrier. You don't find it in its pure form. You rarely find it in its pure form in nature because it is very reactive. That's really why we want it to, because it burns very nicely, right? But it's really in that sense energy carrier, so you have to produce it, and there's many ways to producing it. It really isn't easy to get energy from point A to point B. Fundamentally, that's what we need, right? The problem with electricity is that if you transport it over very large distance, is not very efficient, right? The best way to transport energy in any form is by pipeline with the fluid. On a 500, 600 mile pipeline, you lose about 1% of the energy due to compression costs. If you transport electricity on high voltage line for that kind of distance, you're losing 15 to 20% of the energy. So that's, kind of favors, again, a fluid transport. And that's where you think, okay, hydrogen is ideal for it, but it really has a lot of other challenges.
So Klaus, let's focus in on hydrogen production then. I was wondering if you could give us an overview of the color rainbow and also talk us through some of the key considerations for compression.
Yeah, I mean, hydrogen is hydrogen, right? But a lot of people like to talk about all the different colors of purple, blue, yellow, green, whatever you want of hydrogen. From a practical perspective, there's not that many that are relevant. There is black hydrogen, which is hydrogen produced through a process called gasification from coal. There is gray hydrogen, which is hydrogen produced through typically steam reforming, but it could also be produced from gasification of natural gas. That's gray hydrogen. There is green hydrogen, which is produced from electrolysis. Then finally, there is blue hydrogen, which is usually if you take black or gray hydrogen and then do carbon capture and sequestration. So basically, you separate the CO2 out and stick it in the ground somewhere. That's considered to be blue hydrogen. All of them have some challenges associated with it. 99.9% of all the hydrogen being produced right now in the world is gray hydrogen, basically from steam, methane, reforming. There's very little hydrogen that's actually being produced from electrolysis. There's little pilot plants here and there, but that's not really relevant in the whole scheme of things. So if you take that gray hydrogen, the cheapest form of producing hydrogen, and turn it into blue hydrogen, so you decarbonize it, just from a chemical perspective, stoichiometry, for every kilogram of hydrogen that you're producing, just by chemistry, you'll be producing about 6 times as much kilograms of CO2. That's just because you're starting with a hydrocarbon, right? The reality is actually far worse because you need energy, for example, for steam methane reforming to keep that process going. That gets you to about 10 kilograms of CO2 produced to 1 kilogram of hydrogen. And it gets worse because in the process of producing the natural gas for the methane steam reforming, You have to get that natural gas out of the ground. You have to process it. There's leakage associated with it. So at the end, what you'll end up getting is about 15 kilograms of CO2 for every kilogram of hydrogen you're producing when you're looking at blue hydrogen. It's hard to fathom that you're talking about decarbonization when you're producing 15 kilogram of CO2 that you're producing when you're producing 1 kilogram of hydrogen, even if you sequester that amount of CO2. The only truly green hydrogen is green hydrogen, which comes from alternative energy sources where the electricity is at a surplus, right? If you could take the electricity and feed it into the grid and could actually be used, then it doesn't make any sense to take that electricity and make hydrogen out of it. So it is surplus electricity from wind, solar, hydro that is converted to hydrogen using electrolysis. Unfortunately, those processes are relatively expensive still, and they're not cost competitive with gray hydrogen. And that's why most of the industrial hydrogen that's currently being produced is gray hydrogen.
So Klaus, I wanted to go back to something you mentioned earlier and the importance of the pipeline system. And I was wondering, is the pipeline stream ready for hydrogen then? As the industry grows and green hydrogen becomes more prevalent, how will transportation and storage have to evolve?
Number one, it's not ready for it, but we can start off by saying regionally, there's nowhere in the world where hydrogen is produced in any quantity sufficient to fill a pipeline, even a small pipeline right now. The hydrogen production is relatively small right now. We're talking about the hydrogen transported pipeline that really only becomes an issue when you're producing large amounts of hydrogen, which hopefully will be the case in the future, but it is not the case right now. So then if you look at it right now, there's the option of taking hydrogen and blending it, for example, into natural gas. That's being considered, and there's pilot projects that do that, where you take a small amount of hydrogen and blend it into your natural gas infrastructure. There's hundreds of thousands of miles of natural gas pipelines throughout the world, and you can just put a little bit of hydrogen in there. And that works to a certain extent, but it doesn't work to a huge extent because from a thermodynamic perspective, once you get to a large percentage of hydrogen, you will have to start changing your compression infrastructure. Also, hydrogen will cause embrittlement in your pipelines. So you have to worry about metallurgical effects. And so you can do that with a small amount, maybe 1, 3, even 5% of hydrogen mixed into natural gas, but you really can't take it much further beyond that. And then finally, if you look at the hydrogen or the natural gas pipeline infrastructure in Europe or North America, it is very interconnected. So if you stick hydrogen in there at one point, it's probably going to come out at a place where you don't want it. And if you look at most of our appliances in your house, you probably get natural gas at your house. I get it in my heating system. I get it on my stove. I warm my water with it. None of these domestic systems are actually ready for any amount of hydrogen. Where it is relatively easy to convert a power plant or industry to be ready for hydrogen, it's not quite that easy for the domestic infrastructure. So any amount of hydrogen will pose significant safety dangers if we blend it into natural gas. And that really leaves us with the only other option, which is dedicated hydrogen pipelines. Right? So we end up basically having to develop an infrastructure with pipelines for hydrogen. That doesn't exist. Number two, it's very, very expensive. Number three, there's a lot of safety issues because hydrogen does like to blow up a little bit, right? It has a very wide flammability range, low ignition energy, burns with a clear flame. It's just very explosive. And so it does pose quite a bit of safety risks. So when you put an infrastructure, a dedicated infrastructure of a pipeline network together, you have to worry about that. From a turbo machinery perspective, and that's kind of where I come from, to compress hydrogen is very, very challenging. It is a very light gas and it has a very high specific heat, which makes it difficult to compress. What it does is it requires a lot of power to get a reasonable pressure ratio out of it. From a turbo machinery perspective, let's say you have natural gas and you want to compress a certain amount of natural gas. That may require 1,000 horsepower. For hydrogen, depending on the pressure ratio, look at a couple thousand horsepower. And you will look at a turbo machine that's much more expensive to design and build.
So challenges involved, Klaus, but what opportunities does all of this present for compressor manufacturers?
Well, I mean, it is a new industry, right? And the opportunity and challenges are kind of sort of the same thing. There is a new market for us and we have the capability to design hydrogen machinery. Hydrogen compression has been done in refineries for 50, 60 years. We have compressors that run almost pure hydrogen in refineries. But when you design machinery for a refinery from a safety perspective, you look at it very different than for a power plant or for domestic application. Hydrogen, because it is such a light gas, requires a lot of stages of compression to produce a pressure ratio that you want. So you can address that either by many, many stages, so many compressors basically in a row, or you can address that by developing very high speed machinery that runs very fast. And both of those pose challenges from a design and manufacturing perspective, from a materials perspective. Hydrogen is the lightest gas there is. If you look at the periodic table, that's the first atom that appears there, H and then H2. Hydrogen is diatomic, right? But hydrogen will leak out through your seals and small clearances. And so it is a sealing challenge. As hydrogen is such a small molecule, it does cause what's called hydrogen embrittlement. And so for many metals, it will cause basically the ductility of the surface to change of the metal, which will basically make the metal then very brittle and then easy to break. You get cracks in the surface, and high cycle fatigue and low cycle fatigue, and you get cracks and it will break eventually. And so that's a significant problem. All of these challenges can be addressed. You can use different metals. You can use things like carbon wound fiber. You can use ceramics. You can other things. But there's a lot of R&D challenges and the manufacturing challenges associated with that.
So Klaus, let's talk a little bit about high-speed hydrogen compression, which was the topic of your article, and focusing again on the challenges. Well, what are the challenges to development of this type of technology?
So basically, if you look at a hydrogen compressor, to overcome the challenge, you get a low pressure ratio per head, meaning a low pressure ratio for the energy that you're putting in, for the work you're putting in. You can either put a lot of compression stages and run at a normal speed, or you can make your machine run faster. The tip speed of the machinery increases. So if you want to look at it, if I double the speed of a machine, normal speed runs with a tip speed of, say, 300 meters per second or something like this. If you now double that to 600 meters per second, then you actually can reduce the number of stages by a factor of 4, thermodynamics. So that's great because now you have made your compressor easier, you have made the rotor dynamics easier, you have made the entire machine simpler. But to run it at that speed, you have to have materials that have a relatively high strength to weight ratio. Otherwise, because of hoop stress, the centrifugal stresses, the machine will just fly apart, right? I mean, if you spin something really fast, your stresses will exceed the material strengths and eventually will fly apart. So basically, it is a materials challenge because you're looking at a material that gives you this very high strength to weight ratio. Aluminum is an easy one because aluminum is relatively light. Ceramics, plastics, carbon wound fibers, those are all solutions. Titanium is kind of the obvious one, but unfortunately, titanium is not very good from a hydrogen embrittlement perspective. Generally speaking, very hard metals also tend to have more problems with hydrogen embrittlement because of the ductility change. So you really can't go with really hard metals like Inconels and those kind of things. You can put a coating on them, but coatings will eventually fall off, fail, and so then you're stuck with the same problem. So that's not really a solution. That's from a materials and stress perspective. And then it comes back to the sealing. Hydrogen is a very small molecule. It wants to leak out. And that's not good because it's also explosive. And so when you have leakage of hydrogen somewhere and it lights up, then you have a safety problem, right? When you're also looking at these high-speed drivers, you're looking at drivers that don't really exist. You have to have motors or turbines or something that drives your compressor that has to run at a very high speed, 30,000 RPM, 60,000 RPM, some ridiculously high speeds. And so you need gearboxes. So there is quite a few challenges from the strength perspective, the hydrogen embrittlement perspective, as well as from the driver and sealing perspective that do still need a lot of research development, product development.
So Klaus, can we focus in on some of the technical considerations and talk about how specifications, codes, and standards are evolving to all of this?
Yeah, I mean, from the oil and gas industry, we have the benefit that we have what's called API, American Petroleum Institute specifications that have been around. And because hydrogen compressors have been used in refineries for such a long time, we do have good specifications. Some of these specifications are maybe overly rigorous for other industries, such as the power industry or the pipeline industry. And so there needs to be some adaptation with reason and how they can be used. From a standards and specification perspective, there's still quite a bit of work that needs to be done. From a technology development perspective, we can make a hydrogen compressor right now. It's just not a very cheap and not a very efficient machine. So the technology development that needs to happen is higher speeds, which implies different materials, different coatings, different drivers, different sealing mechanisms. We're still kind of sort of on that development curve that will need a couple of years. It is, and this is important to understand from a manufacturing perspective, there's one thing, which is the R&D guys developing a machine and coming up with a design. That's just part of the entire picture. You also have to then modify your entire manufacturing and service infrastructure, right? It's relatively easy to design something and say, here it is, but you still have to manufacture it. So you need new manufacturing capabilities for this. This also goes back to the total world capability of manufacturing turbomachinery. If you look at large industrial process compressors, there is a number of large manufacturers. There's us, there's our competitors. The total number of compressors that we can manufacture is maybe around 500 or 600 per year. If you look at our capabilities and everybody else's capability. And all of them, by the way, are being used right now by somebody. And so now we're being asked to also make all these hydrogen and carbon dioxide and ammonia and all these other machines for an industry that is still somewhat hypothetical, right? Because there is no hydrogen economy out there right now. There will be, and I think we all believe that there will be. We are transitioning. We're spending quite a bit of capital resources in developing this machinery, but it's also a significant step for a manufacturer to say, we are going to take our manufacturing and service capabilities and prep them for a market that doesn't quite exist yet. So that's a significant challenge because it's not just product development, it's everything that goes along with that.
So when we do get there, the benefits of a hydrogen economy are fairly obvious. But I was wondering if we could touch upon some of the risks involved. I know, Klaus, you've already touched upon these and mentioned it a couple already, but maybe you could just give us some more details about some of the other risks that we're looking at here.
Yeah. I mean, we talked about the technical stuff, right? And the technical side is manageable. And I talked about the manufacturing side, and that's the manageable with money, right? I mean, you have to obviously create a demand for these machines. And then there is a safety aspect. And the safety aspect is not just pure hydrogen. You will end up with situations where, there will be accidents and then people will blame other people and new technology. That's always what happens. With hydrogen, you have to worry about that. You also have to worry about the same thing with hydrogen carriers, like ammonia, right? As I mentioned, ammonia is toxic, caustic, et cetera, et cetera. And so there will be accidents and people will be unhappy. Methanol is another hydrogen carrier and is also poisonous. So there's always pros and cons and risks associated with this new technology that you have to at least evaluate and take into consideration. With hydrogen, those risks tend to be higher, which means you have to take more precautionary measures when you're dealing with hydrogen than, let's say, with natural gas or other hydrocarbon fuels.
So, Klaus, a final question from me today. And I was wondering if you believe that there is a mismatch between the vision for the energy transition and the current reality. What do you consider to be the realistic considerations and expenditures going forward, given factors such as geopolitics, market demand, etc.?
There's a mismatch as far as the expectation that we're going to be there by 2050, right? That's not that many years away from now. I think the world is moving in the right direction. There is a build out of wind and solar. There's more hydro. There is energy storage coming in. And that's obviously necessary. When you look at these intermittent energy sources, there is also a pilot projects on the hydrogen side. And all of that is moving in the right direction. I think the time frame and the expectation that we'll get there by 2050 is probably not realistic, but I hope it will happen in my lifetime still. It's certainly something that needs to happen because otherwise we're moving toward a higher carbon content in the atmosphere and we don't really know what the consequences of that are. But yeah, I mean, I think the biggest challenge is that a lot of infrastructure needs to be built out. The global manufacturing capabilities, not just on our side, whether it's just the turbo machine, but it's also the pipeline side. It's also the electrolyzer side. It's also the energy storage side. There's a lot of pieces of equipment that are technically possible, but you don't have manufacturers or adequate manufacturing capabilities available for those. And again, just talking from a turbo machinery perspective, we know how to build these machines, right? But you can't just transition from one product to another. And building a turbo machine is a complicated thing. Not everybody in the world can build it. There's a lot of technology that goes into that. But you can't just build one plant after another that starts building compressors. It takes some time. It takes a lot of money. A lot of those investments will have to be taxpayer or ratepayer based, right? And people don't like that because people don't like to pay extra money. And so those are some of the challenges that will keep us from meeting these goals by 2050. But I think we'll have a fair chance of meeting them sometime thereafter.
Klaus, thank you so much for taking the time to explain your article in more detail for us and really dig into this fascinating and timely topic. Really grateful for your expertise on this, so thank you.
Well, thank you very much for talking to me, Colin. I really enjoyed the discussion and looking forward to hopefully another one in the future.
My thanks once again to Klaus Brun for taking the time to dive into the topic of high-speed hydrogen compression with us. As mentioned, this was the topic of a recent article that Klaus authored for Hydrocarbon Engineering magazine. This article is freely available to access now. If you already have a subscription to Hydrocarbon Engineering, simply log into your account over at our website, hydrocarbonengineering.com, to download your copy of the February issue. Or alternatively, you can register for a free trial subscription to Hydrocarbon Engineering by visiting hydrocarbonengineering.com/magazine and following the simple on-screen instructions. Thanks again for listening, and if you enjoyed this episode, please like and subscribe.